Thank you for your introduction, Steve. All right, so what I'll try to sort of give a bit of background to what I hope to sort of what my big goal is in this talk. In Princeton last year, I gave a talk on Rota's conjecture, and the thing about it is that Jim, Bert and I, as everyone knows, we've been working on the Matroid Miners project for 15, 16 years now. But that project is really to sort of obtain results for matroids representable over finite fields that generalise in the results from the graph miners project. And the thing about it is that Rota's conjecture is not a theorem, is not a conjecture about representable matroids, it's a conjecture about matroids that are not representable, minor, middle, not representable. So, and the results of the Matroid Miners project are massively technical, and it's just going to, I think it will be, I think conservatively, if I live to see them all published, I will be very surprised. I mean, I will make Henry look like a youngster at this stage. And I know this, and I mean this honestly, because there's a paper that effectively I did most of the writing up for, and it's called Inequivalent Representations of Matroids over Prime Fields. And Jim and I announced that result. We knew it was true, we knew how to prove it. We announced that result, and I basically used every bit of spare time for writing up over a period of about 7 years. Perhaps it was even 8 years before the whole thing. And it was meant to be a series of papers, but it ended up being one long 200-page paper, and that took a lot of time. So actually it will just plain take a lot of time for this technical crunching, grinding, having to go through all of the horrors of the details, as anyone knows if you look at the graph miners papers. So the question is, if we accept those results, and I'm not asking anyone to accept those results, right? But if you were to accept those results, how would you get Rota's conjecture as a consequence? And then that is normal mathematics. So if you accept certain things as you can put these things as in a saying, well, I'm not going to accept, I don't know whether I believe what Geoff and Jim and Bert say about the Matroid Miners project. You're free to make that choice. I don't care either way, to be honest. But the thing is that what I do care is that to say, if you accept those things, then you can prove Rota's conjecture. And that's what the purpose of it is. All right, so I know what I'd like to do is to give you some insight into that process. So we all know Rota's conjecture, I'm sure. For any finite field, there's a most finite number of excluded minus representability. So throughout this talk, I want to imagine we've got your favourite finite field. No, not your favourite one, there's probably Geoff too. Well, it's not my favourite one. My favourite one's Geoff3 for some reason, right? But, so you fix your favourite finite field and make it relatively large. Geoff11 is a good one. And let's just, so that's, F stands for a fixed finite field. And what we're going to do is look at various things. Now, the ingredients of the proof are that we get certain things that are consequences of the structure theorem. So they're the theorems from the Matroid Miners project. So and so we need those. The second ingredient is to say, if Rota's conjecture fails, it must fail on a matroid that is in some sense very highly connected. So if Rota's conjecture is false, there must exist arbitrarily large matroids that are excluded minus that are in some sense highly connected. And that was the topic of the talk that I gave in Princeton a year ago. And that's, in the paper that I've just finished writing up, that was about half the paper. So now what you have is, so that gets us that we've got, if Rota's conjecture fails, we've got this huge excluded minor that's in this in some sense highly connected, and a lot of the talk will be about what we precisely mean by the highly connected and how we use that notion of connectivity. And the last part is which I'll talk about today, is to say, okay, and then we use techniques that generalise those in the notices paper, the paper that Henry was talking about before, that we wrote, which is a short sort of that paper indicating some of the techniques. And the point about that paper was, in that paper we gave an actual proof of 3, But the connectivity that we used was enormously artificial. We said the enormously artificial connectivity that we had, which is not a hypothesis that we can make, was that we showed that there were there were a finite number of excluded minors with massive, and whereby massive I mean massive in the sense that the number of atoms of the universe is some trivial number, right? So we're talking about very, very large. And that's our tut connectivity, right? And so tut connectivity is, 3 connected, 4 connected, 200 trillion connected in that exact tut sense. So that's a highly artificial thing because there's no way that you could ever prove that excluded minors must have that connectivity. But the point was to get an insight into the techniques. So what I'm trying to do is do what goes on in the last part, in the notice paper, but with a connectivity that we can actually achieve. So that's the goal of this talk, in some sense. But I've got other goals in this talk too, and so it's all going to get confusing. I very much like if people interrupt me. Like everything else, it's all about connectivity in this world, and I'm sure that you're sort of familiar with this diagram. I think we've talked about this. But I don't think about, you don't want to think about connectivity here as sums. You just want to think of connectivity here as a connectivity function. You've got a subset and you've got the complement of the subset. And it's just telling you about the rank of the space that those two subsets are looking at, and that rank is somehow a measure of how much interaction can go on between those two subsets. But that's all that we mean by connectivity. Whoa! I was thinking, people are putting the number of slides on their talks.
Comes up.
And I was thinking, that is a bad rule because you can just sit there and think, oh no, there's at least 30 slides to go. How long is this talk going to go on for? And someone's programmed this thing to do something terrible. Okay, so now I'm going to be talking about something that is increasingly something that obsesses me. Is that I think if you want to work in this type of world of extremal Matroid theory, in the sense that it's extremal Matroid theory because we're trying to prove we can make the objects that we're working with arbitrarily large, and we're sort of being qualitative because when we prove Rota's conjecture, we're not going to prove anything like, we're not going to give you a computable bound on the size of an excluded minor. We're just saying, that there's only a finite number. So we're only talking about the distinction between the world of the finite and the world of the infinite. So our numbers are going to be arbitrarily large, and our techniques can be highly qualitative. And when you're in that world, you for sure need to think about what a very, very large generic Matroid could look like. And if you're used to thinking of Matroids from your models of a Matroid, as in almost always in some sense as very small things like Matroid of K4 or these sorts of small Matroids, then you're a long, 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 long way away from that world. So it's very much like, what's that subject in physics where theory of gases, and there's a fancy name for that particular subject. Or fluid dynamics, what we're looking at is if you're used to thinking, if you're a chemist and you're thinking about the molecules, then you might not have a good approach to fluid dynamics. And yet fluid dynamics is made up of molecules, and it's actually spawned by the way that the molecules are interacting, right? But actually fluid dynamicists, whatever their names are, they're not thinking about that because they've sort of removed themselves from the world of the molecules a long way away, and they're thinking, in this case here, it's not fluid dynamic, but they're thinking of some very, very large object of which the molecules are some incredibly tiny part of. And so that's really the way you want to think about Matroids for this type of thing. And if you want to think about Matroids from this type of thing, I've got some math. But notice, by the way, that it is important to go down to the molecules because how the molecules interact with, almost all the proofs, you'll be thinking some arbitrarily large thing. But if you want to prove something to be arbitrarily large thing, you'll have to start by looking at the way the molecules interact to show that some upward induction spawns the right global structure in the bigger picture. I'm just saying these things because that's how I've had to learn to think to be able to do part of mathematics, which I find very difficult at the start. And so if I think in an arbitrarily large matroid, and so here it is, and I just want to generically represent it, and I'm representing it in such a way that I'm not saying much about what's going on, but what I'm trying to indicate there is somehow what the connectivity might look like. And this is actually, I know this picture is not misleading. This picture is a representation of something that's a theorem. And the theorem says that if you give me an arbitrarily large matroid, it is a tree-like structure of pieces that are highly connected in some sense, but with, in some sense, relatively low-order separations separating. So it's not that an arbitrarily large matroid is highly connected or not lowly connected. I mean, and of course, ordinary notions of connectivity are really stupid in an arbitrarily large matroid. So if someone said, oh, look, here I've got this matroid and it's really large and it's got tap connectivity 200 trillion. And then someone said, oh no, look, I'm going to ruin it for you because I'm going to add a point in parallel to one. Am I changing what's really going on in that world? No. So we can't use, we've got to find a much more effective qualitative way to understand connectivity. And so what we've got is if we think of an arbitrary large matroid, the typical phenomenon will be that we'll have some blobs that in some sense highly connected, in the sense that there's no way that I can partition this and in that partition give me low values of the connectivity function. Right? But oh, look, I found a place here where I've got a low value of the connectivity function. And I mean, max flow min cup, right? You found a small cup. Whoa, you found a place where there's, and so it's just all the same look. But we've got to sort of, that's the generic thing that we want to think about what our matroids are like. If you think about this world, you don't want to think, oh, is it like Q6 or whatever. Okay, so I've talked about type connectivity, and I'll just said that in the notice papers we gave a version of the proof for type connectivity. Okay, so the next thing is, what is the connectivity that we actually get for an excluded minor? The connectivity that we actually get for an excluded minor is a thing that we call F connectivity. And F connectivity is just a terrific notion of connectivity, really. And what it says is, particularly when you get into the world of very large matroids, and what it says is, so for K separation, so K is something that's just this, we're talking about a function, and for all K, there exists, you just take an integer valued function, and a matroid is F connected, if whenever I take K separation, then one side or the other has at most F of K elements. So you'll have a zero separation, so if I take an actual separation, one side or the other has at most F of zero elements, and so on. So that's F connectivity. Now, in some sense, F connectivity, so for example, if F of 2 was 1,000, F connectivities doesn't seem to be very strong. Or if F of 4 was 200 million, F connectivity doesn't seem to be very strong. And I have no idea what the F connectivity that we can use here for proving Rhoda's conjecture. Now, what was said very well, so I'll come to that in a minute. What the theorem that I talked about, so this is the theorem I talked about in Princeton last year, is if I give you an excluded minor for F representability, then for all K, there exists an N such that if A, B is a K separation, then either A has at most n elements or B has at most n elements. Another way of saying that theorem is that if you give me an excluded minor, there is a function F such that N is there is a function F, such that all excluded minors are F connected. Now when I say all excluded minors, I'm talking about all excluded minors for the fixed field that you've got in the back of your mind, right? So that field is fixed throughout this field. So that says excluded minors are F connected. It doesn't say that that function is very nice. In fact, the best that we could do would give you a function that would be scarily horrible, and that's the point. But what it does, I mean, in some sense that doesn't matter, it just all filters out. Okay, so that's what we know about excluded minors for this talk. All right, so so now we've got to the goal of this talk, which is to outline a proof that F-connected Matroid excluded minors, and that's pretty much what I've been talking about. All right, so as well for this talk, what I'd like to do is distinguish between those things that I can tell you that I can prove in the sense that I can give you a written out proof for, and those things that you have to take on. I said this in Princeton and I regretted saying it, but this is a smaller group between close friends. This is things that you have to take on faith-based mathematics, right? Then we'll call those hypotheses. So I'm just going to show you the hypothesis we're making.
Move towards the middle.
Oh, I'm out. Oh, that's good. So things that we'll call hypotheses. Okay, so these are the outcomes of the Matroid minus project. The first one is, I'm sure that you're all familiar with this, that F representable matroids are well quasi-ordered under the minor order. Now, we're not going to need this one for this talk, but not everyone was at Princeton, so I feel that it's good to sort of mention this. I'd say that when we actually write when we come to actually doing a version of Rota's conjecture, which is actually a proper one, where these hypotheses are no longer hypotheses but theorems written up and submitted, we actually probably won't need that hypothesis, but that's the current version of the proof we've got does need that hypothesis. But we don't need that for this talk. We need this hypothesis to get that excluded minors are F-connected. So but I just want to mention that. And by the way, someone asked about rooted binary matroids, and this hypothesis is also true for rooted matroids where you have a fixed root set and the minors have to preserve the root set, and you actually need the root, the version needs the root version, but I'm not going to go into that. Now, to state the next two hypotheses, the most efficient way to state them is that I want to talk about tangles, which is the way of identifying a highly connected region in our very, very large matroid. And these big blobs are identified by high order tangles. So a number of, I'm aware that this will be a mix of people who know what a tangle is and who don't. So for those of you who do, just sort of nod off for a little while. I actually think that this, to my mind, is one of the most brilliant ideas in the whole of the Graph Minus project, of saying I want to identify a highly connected region in a graph. And if I want to identify, say, Manchester, if I take the road map of England, Manchester is a highly connected region in the road map of England, like you'll just see it. And if you look at a sort of a picture of England taken at night from outer space, you'll see the high connectivity, because you'll see it's this. But how do I recognise that high connectivity? Well, I can't actually recognise that, or it's a bad idea to try to recognise that highly connected region as a subgraph. That's a bad idea. Because if I throw away all of the roads in England, except the roads that are efficiently in Manchester, I erode the connectivity in Manchester. And everyone who lives in Manchester will know that, or they'll say, oh, if you want to get from here to here, I wouldn't drive through town. I would take the back route and go blah, blah, blah. In other words, connectivity within Manchester is perfectly entitled to use the rest of the road map of England to gain connectivity within Manchester. Effectively, or another way to think, if I take two vertices in Manchester, not connected by an edge, but if there's a road that goes outside Manchester and goes through some other things, that effectively adds to the connectivity between those two things. So you can't ask for a naive way like that to identify a highly connected region. So how do you identify a highly connected region? And I don't know how. I mean, Seymour's a mysterious person and how he ever thinks of the things he does. They said, what you do is I claim that my region is highly connected, and I believe it's sort of roughly represents is something of connectivity. Theta, forget about the plus ones and minus ones, because I'll definitely be wrong here, because it changes according to the way there's this horrible plus one that slips in and out, many of you will know. But say I think, oh, this is about of order theta, this, that theta connected this region. So what I'll do is, I'll say, I'll look at every subset of edges. I'm saying this in graph terms because I was thinking of that model with Manchester, but let's do it for matroids and you can make it. So I'm now looking at a tangle in a matroid, so I'm trying to identify a highly connected region of the matroid. So for every set of elements of the matroid, if that lambda is the connectivity function, if the connectivity function of that set is less than lambda, so that means it's anything from 0 up to lambda minus 1, say, well, everything in it, so I'm not saying this very well, I haven't written those ones very well. So what you're saying is, a better way to say it is, I look at every separation of order less than theta. So, and now separation is a partition AB in the matroid. And for every separation of order less than theta, exactly one side belongs to the tangle. And so the tangle is actually a list of subsets, and they're what we would call the small sides of the separation. And I always thought that this is very wrong, because a tangle is identifying a highly connected region. And Robertson and Seymour defined the tangle as being the small, what they call the small sides of the separation. What's really happening with the tangle is, in this particular, say if I look at this blob here, so Robertson and Seymour thought of what I think of as the small side as being pointers. And they say, so am I trying to identify this highly connected region here? And you give me a small separation, say it's this one here. And I say, okay, which side of the separation, so that's my separation there, and that stuff there, which side of the separation is the highly connected region I'm trying to identify? Which side is it on? It's over here. In other words, this side is a pointer to, if you want to find the highly connected region, go there. And that was what was in their minds. And so I'd look at this separation here, and I say, oh, okay, if you want to get to that highly connected region, go there. So they think of these as being pointers to where this highly connected region is. And every small separation has these pointers. And so that's all this is all saying. And the crucial one is that you can't cover the matroid by 3 small sides. Now the thing about that is, if you could cover the matroid by, why do you need this one here? This is the one that really gives you traction. Why do you need that one there? Well, if you could cover the matroid by 3 small sides, what that would mean is that you would be able to take this set here, and if you, it's an easy exercise, so if you can cover it by 3 small sides, you can partition the matroid into 3 small sets by some modularity, blah, blah, blah. And that would mean that what you'd be able to do is put a small set there, a small set there, a small set there, and draw a little graph with a vertex there, and edge going to that small set, and edge going to that small set, and edge going to that small set. And the connectivities on those edges induced by those partitions in the matroid would all be small. And if you know what a branch decomposition is, what have you done? You've started to build a branch decomposition of the matroid. And that's a matroid that's got so if you don't know what branch decompositions are, don't worry about it. So a matroid that's got and then and also notice what I've done is apparently the region I was claiming to be highly connected splits up with these small separations. Well, hey, that's not what you would want to see in a highly connected region. So, if you know about, if you just think about that for a little while, you'll understand basically. That's what you need to think about if you want to understand the duality between tangles and branch width. But it's also, you'll see the necessity for this. If you're saying this highly connected region, you shouldn't be able to split it up with small separation. Okay, so they're the technical axioms for a tangle. And the frustrating thing if you're a beginner with tangles is that the technical axioms don't seem to capture what tangles really are. But hey, we're matroid theorists. if you show anyone the independence axes for a Matroid, and you say, this captures geometric configurations, any reasonable student will say, yeah, right, whatever. I mean, you have to learn that it captures it. And you have to, I mean, that's part of, we all have to do apprenticeships in whatever we do, and that's you just have to suck it up and deal with it.
Geoff, sorry, if you took the third action and you changed it to 4 sets or 10 sets, would you be asking for some kind of branch decomposition into a higher degree tree?
That's a very good question, and I'll pay you later, because that's a very good, why 3, why not 4? And actually, the thing about that is, that's if I were to make that 4, then that would be dual having branch decomposition, where I'll be allowed 4, instead of having a degree 3 tree, I could have a degree 4 tree. And there's a thing called the covering number of a tangle too, which is the minimum number of small sets that can cover the things in the tangle. And that actually gives you another parameter associated with the tangle, which really tells you how robust that tangle is too. And those things are important. They're interesting and important. And if you want to talk about that stuff, you should talk about, gosh, his name's just slipped my mind, but the other student of Jim's who just finished a PhD. Because he knows a lot about that sort of stuff. Okay, so that's tangles. And I've said, the small sets, but anyhow, I'm not sure if I'll need that. Now, the other thing is that what we can do in a tangle, and in fact, this to me is the most useful way to think about tangles. Once you get a tangle and you get this sort of stuff, is that we can define a thing which is the rank of a tangle. And what's that? Well, I've got a definition, but I don't care about saying that. So, the rank of a set, right? So, if you give me a tangle in a Matroid, so now I've got a particular tangle in a Matroid, and I'm looking at everything with respect to that tangle. So, focusing on a particular highly connected region, I'm looking at everything with respect to that particular highly connected region. So, in this picture here, this is the highly connected region I'm trying to latch onto. And then I'm saying, well, okay, I'm going to give you a set. Just so happens the set I'm looking at is this set here. And I'm saying, what's the rank of that set? And then what I do is I'll say, I'll look at the smallest order, I'll look at the biggest set that contains this, with the smallest, it's the minimum of the smallest order of a separation that contains this, for which this side is small. Right, so it's, I mean, that the big side's got to be on the other side. So here, here I've got a separation of order 12. The big side's over here, so this is definitely small and it contains it. So that's a proof that the rank is less than or equal to 12. But actually, here's a 7 separation, and that's a proof that the rank is less than or equal to 7.
What's the rank of a set that isn't contained in the small side?
The rank of a set that isn't contained in the small side is, I haven't put it there, but that's the order of the tangle.
Yeah.
So you know, I mean, yeah, that's a good question, but so the interesting question to ask is how do you calculate rank when it is contained in the order of tangle? So what do you do in this sort of stuff? Another one, so that tells me that this set here is rank 7. So, and that's a sort of like a Menger theorem, isn't it? Right? You've got this, you're sort of looking at how much, the rank is a measure of how much capacity for Mengering you have to this other side, which you think is being highly connected. The beautiful thing about that rank, and it gets dusty here, tears almost come to my eyes, except, I've written it there. I thought I had this thunder prepared. Obviously this is bad slide writing, I'll have to get better at it. The rank is the rank of a Matroid. That gives you the rank function of a Matroid. And it's a sort of, and this is true for graphs, by the way. It's one of the really nice ways that Matroid theory should be interesting to graph theorists, even if they don't care about Matroid theory, right? Because it's really the rank function, the tangle matroid is an interesting matroid, and Robertson's specs about the tangle matroid lots. Okay, so that's, so if I tell you that, what could you say about, so if it's a matroid, it must have a closure operator. Can anyone tell me what closure in that matroid would be?
A maximal small site that contains the set, maybe? No, a minimal small site that contains the set. No,
It's actually the set whose separation is the smallest separation.
It's the, yeah. So Rudy said it's the set whose separation is the smallest separation. And he's almost right, and I'll give him.
It's the X in there, no?
well, the minimal such.
The X in the rank.
Not the minimal such set.
The minimal such small side with the smallest possible lambda.
What's the maximal set?
The maximal
No,
X.
Yeah.
Maximal
So
minimizer.
if I make this a
It's
sentence,
the
so
largest
these are
X
both
that you use
sevens,
It's a
right?
maximal minimizer.
Yeah. So if I make this both sevens, then it's actually this is the closure.
Yeah.
So you gobble up as much as you can without increasing rank. Oh, that's the definition of closure, right? Okay, so I gobble up as much as I can without increasing rank, and then I get to there, and then all of a sudden I notice that and notice in that, I mean, that's, so, and actually being closed, having closed sets in a tangle is terrific, because it tells you that where I am, there's no small separation that separates me from the highly connected stuff, and that's good news and powerful stuff. Okay, so that was sort of like, all of that was just a pitch about tangles, because I just want people to tune into tangles, that's all. And now I'm just going to say this quite quickly because we don't really need it. So fragile elements, I think just about everyone here knows what fragile elements are. If you don't worry about this because it's not important. But an element is fragile if you've got a minor. An element is fragile if you lose the minor by either deletion or contraction. And in this sense here, for those of you who care about fragility, notice that I'm saying as a minor, not isomorphic, not an N minor. I'm saying that you actually keep the exact minor. And that's hypothesis 2. Now, this is how hypothesis 2 goes. It says there would be an F representable matroid, tau be a tangle in N, and then the set of N fragile elements has bounded rank with tau. And notice that using tangles gives you a way. I mean, this is a consequence of the Matroid Minus project. But what I want to say here is using tangles gives you a way to say something that would have been very, very difficult without tangles. There's no way, you cannot control the number of fragile elements. And not only that, the fragile elements have to be here, there, and everywhere. They can be all over the place, and if you've had anyone who's worked in fragility at the molecular level knows how horrible life is at the molecular level with fragility. But here we're talking up at the fluid mechanical level, right? And when you get up there and you don't care how far up you've gone to some vast distance, if you've gone, you're up at the fluid mechanical level, then the fragile elements all just turn out to pile up into some. So, for example, there's some the fragile. There has some bounded rank set, and all the fragile elements are trapped in that bounded rank set. And so that
we usually bounded.
Right, it's bounded.
It's the
So
fields, it's the order of the angle.
Yeah. Okay. That's. I'll pay Peter for asking his question. I'm not going to pay you. But all right, because I didn't really want to talk about it. But let's think about it. So what we've got is we've got our fixed field F. So it's a function of various things, right? We've got a minor N. So and then it's there. So we'll say for all F. So the parameters are the field and the minor, and there is a function of the field and the minor, and that gives me some T. And then in any tangle, it's independent. The T is independent of the tangle. It depends on the field and the minor. So this works. So that's the important thing there. And so, but anyhow, so that's just for those of you who have an interest in, because again, that hypothesis is not needed for this part of the proof of products conjecture, but it is needed for the other part. So relaxation is a phenomenon that most of you are familiar with. You take a circuit hyperplane, and it's been talked about already here, I believe. You take a circuit hyperplane and you declare that it becomes independent. Now relaxation is interesting for various reasons. One way or another, relaxation appears in every proof of Rota's conjecture that up to now, for GF2, GF3 and GF4, what you effectively get is this, you effectively get, you do stuff and then you effectively get, I've got two matroids here and they're meant to be both be representable over the same field, but one's a relaxation of the other. And then you've got something that says, you've got some lemmas that say that certify that modulo certain hypotheses, you can't have that. So what that, and so you relax the circuit hyperplane, but notice that the property that we get when you relax the circuit hyperplane is that we've got two different matroids, M1 and M2. If you take them, you kill the difference between the two matroids either by deletion or contraction. So it's easy to kill the difference. And if we just forget about contraction, it means there's a lot of elements whose deletion gives me the same matrix. And now that's going to be important for us. Relaxation doesn't behave well with respect to representability in the sense that very often if you relax a circuit hyperplane, you get a representable matroid, you kill representability. For example, if I relax a triangle in the Pappas configuration, I get a non-Pappas configuration, and that's typically, or Desargues non-Desargues. Vamos, exactly. So this is how the typical examples that we know about non-representable matroids are obtained. But hey, what about wheels and whirls? A whirl is a relaxation of a wheel, and both wheels and whirls are representable over pretty much any field you like, except GF2. So that's not always the case, but we do know it's sometimes the case. Okay, so hypothesis 3 says this. It's a sort of it's a way of capturing that two representable matroids cannot be too much alike. Over a finite field, right? And so let's see if we can decipher what this says. It says there exists an integer h, and Rudy, I'll leave you to work out what h is a function of. But so that if I give you two f representable matroids on a common ground set, and oh look, I've got to talk about a tangle for it to be possible to state this theorem. I wouldn't know how to begin to state a theorem like this without a tangle. I've got a tangle in, then and I take the set of elements whose deletion kills the difference. Right, so I look at the set of elements whose deletion kills the difference. Then that set of elements has bounded rank in the tangle.
What's M in the statement?
Deadline.
Oh, okay. It's either M1 or M2, whichever you prefer. Right. Okay. So I've got two different matroids, and I've got a tangle in one of them. That's a typo. It should be M1. It's meant to be M1. And I take a tangle in M1. Notice that if I can kill the difference, then I've essentially got the same tangle in both matroids. But I'll just fix a tangle in M1. My apologies for that.
And the rank is in the tangle.
Oh, yeah. My apologies for that too. This is what happens when you try to do a talk on an iPad. iPad mini, by the way. It really did stretch my capacities to the limit. So that's the rank in the tangle. So that's the important thing to know, that this set here can have arbitrarily large rank in the matroid. Right? I can give you a wheel and a whirl. The set of fragile elements has arbitrarily large. I mean, and everyone knows you can do all sorts of things to build arbitrarily large rank sets of fragile elements. What this is saying is that the rank in that tangle is bounded. So what it's saying is if I give you some big highly connected blob in the matroid and look what else is around, the set of fragile elements has relatively low connectivity to that blob. It's all trapped on some small side of separation. And that's the way to capture how fragile elements are forced to behave in a long way. This is a lot of work. In the actual proof of Rota's conjecture, I mean, to prove this, you've effectively got to go through the whole of the work for the structure theory for matroids at each of the three levels, the different levels. I don't want to talk about that, but you've got to do it and develop a simultaneous structure theory for two representable matroids. And you would think you could just sort of, use a technique that's a familiar one, familiar to most of us. You use what you already know and try to understand that, but no, there's work and it's a paper. All right, so they're the sort of the hypotheses, but it's the last hypothesis that we'll use. Okay, so now we're back to F-connected. Now I just want to start to say a few things about F-connected matroids. First of all, there's some terminology here that is, if I give you two functions, I'll say one dominates another if it's always greater than or equal. The values are greater than or equal to for all x. Now notice many theorems for F connectivity will actually be true if I replace F by some function that dominates it, right? I mean, because if I tell you that, if I prove that excluded minors are F connected for some F, then if you're F connected, you're also F prime connected for anything that dominates you, right? That's sort of like genuinely easy. So that tells you that excluded minors are F prime connected for any function that dominates. So that's good. You can just flick from, what that means is that if we get things about F connectivity from one place and we get things about F connectivity from another place, F prime, we can put them together by choosing functions that dominate, right? It's a triviality and I just need to mention it to move on. Okay, now the thing is that let's think about what goes on in the excluded minors for say Geoff 3 or Geoff 4 or one of the ones you know. You all know that you start off by having lemmas, and the lemmas say, oh, lo and behold, this is one of the reasons why you care about proving things like splitter theorems, right? What you try to do is you try to say, here's my excluded minor, and then you try to say that there are elements that I can remove to keep some form of connectivity. And often you want to keep a minor as well. Turns out in what we're going to talk about, we don't care about keeping minors. And like you're in this you're at the molecular level, so you might only find one or two left. You're only happy with one or two. But hey, we actually want to be able to remove arbitrarily many elements from our massive thing and keep connectivity. So we've got this huge excluded minor that's F-connected, and it turns out that our techniques force us to want to be able to remove a whole bunch of elements to keep that connected. But we can't do that. We can't do that. But we can get close. And before I talk about it, there's something that's similar to F-connected, and it's all part of the same conceptual world, except it's FK connectivity, and here K is some fixed thing, and so a matroid is FK connected if we just have the restriction that we have small sides, we have bounded size separators up to K, and then beyond K we don't care. Right, so that's just that. So you just have to, we often switch between F and FK. We know excluded minors are F connected, but some of the outcomes of the lemmas will just, we'll get FK connectivity. Now the thing about it is, if I'm F connected and I think about tangles, then what sort of F connectivity is really saying is so I've got this huge F connected matroid and I'm looking at, say, small separations up to size, just 1 million or something small, then the separators are all small on one side. Well, here's a good way of defining a tangle, isn't it? You give me an F-connected matroid, and I'll look at a K separation, and I'll say, I have to decide which are the small sides and the big sides of that tangle. So I look at a K separation, and I'll say that the small sides are the sides whose size is less than or equal to F of K. Now that process will be unambiguous and give you a well-defined tangle for an FK connected Matroid, so long as the Matroid has more than 3 times f of k elements, right? Because if I give you a k separation, you can't have both sides being less than or equal to f of k, and I can't cover the Matroid with 3 sets of size f of k because I've always got one left over, so at least one left over. So that's cool. FK connectivity gives me an obvious tangle that I can focus on. Now you might think it's the only tangle in town because you've got this small stuff, but actually the small stuff is not that small. This small stuff is, there could be all sorts of tangles and weird things going on in the small stuff. So it's not the unique tangle. So I do need to talk about the tangle induced by FK connectivity. That's a well-defined tangle, and this is true for F connectivity. If I just tell you a Matroid is F connected, then there's a unique maximal tangle because I just take the maximal k such that the Matroid has more than 3k elements, and that's my thing, right? So that just tells me that these connectivities give me tangles. And finally, we've talked about tangle independence and tangle closure. Sorry, tangle rank and tangle closure. Obviously, there's a notion of being independent in the tangle. And if you want to think about independent in the tangle, what that means in a graph theoretic sense is a sort of, think about it from a memory point of view. If I've got this highly connected region in the graph, and now I've got this set of edges, and being independent in the tangle means I can contract that edge just boom, onto this highly connected region, and they'll stay as an independent set of edges. They won't form any cycles. There's no small separation. Tau independence is an incredibly strong property. It's a wonderful property. It means you're independent and co-independent. You can't separate. So you get a lot of stuff in tau. So we're still looking to find connectivity that we can keep. All right. So let's. So finding connectivity we can keep. We've got a function with f of 0 equals 0 and f of 1 equals 2. Now we're starting off with an excluded minor. Now with an excluded minor, what can we say about f of 0? We know an excluded minor is f connected. But we can say a little bit more. We can say what the value of f of 0 is. What's f of 0 for an excluded minor?
It's connected Matroid, so it better be 0.
F of 0 is a connected Matroid, so it better be 0, right? And that's true. So we can assume that for what we care about, we've got a function with f of 0 equals 0. What can we say about f of 1? There's a theorem for excluded minors of Matroids over finite fields.
3 connected, so it better be 1.
Better be 1. And it's, so 3 connectivity is the statement in F connectivity that f of 0 equals 0, f of 1 equals 1. There's some technical reasons because we want to apply certain lemmas where we can't assume 3 connectivity, so saying that f of 1 equals 2. So we're actually taking the weaker assumption here that Eric, you might think of that as if we're being a bit weaker. No one actually showed us the lemma that excluded minus the 3 connected. They just showed us the lemma that excluded minus the 3 connected up to series and parallel pairs, right? Anyhow, here are some auxiliary. So I started with a function like this. Here's 2 auxiliary functions that I'll get. I'll get one. I'm going to stop in a minute, even though I've got a lot more stuff prepared. There's this function f twiddle, which is just defined by f twiddle n is equal to f of n plus n. Now this f twiddle is going to arise in proofs. We're wanting to keep connectivity, and we'd like to remove a whole bunch of elements to keep our f connectivity. Oh dear, how sad, never mind. We can't do that. Well, it's even stronger than that, what we want to get. We can't do that, but what we can do is we can get this f twiddle connected. But f twiddle connectivity is problematic because in this case we get f twiddle 1 is equal to 3. Now we've got f of 0 equals 0, we've got f twiddle 0 is equal to 0 if my calculations are correct. We've got f twiddle 1 is equal to 3. Now f of 1 equals 2 is not problematic because we just have series and parallel pairs. Well, hello, are they problematic in this world? No, because they don't affect the number of inequivalent representations of a matroid, you know, so it is canonical. What's problematic about having f of 1 equals 3? That means we can have two separating sets. What sort of two separating sets could we?
Maybe do a 2 sum with a U2-4?
Ah, right. We can have a two separating set, so we've got our matroid here, and we can have a two separating set consisting of a 3-point line looking at that. Well, that 3-point line is a triangle and a triad, and so I call those things triangle triads. And that's summing on a U2-4. What happens when you sum on a U2-4 in terms of, for those of you who know about inequivalent representations, if I give you a matroid which is uniquely representable over, say, GF4, yeah, but I don't want to say GF4, I'll say GF7 just to get away from an issue with GF4. And, oh no, GF4 is exactly the one doing it right. And, but anyhow, and I sum on U2-4s, I just create this world of arbitrarily many inequivalent representations. So I can have, so this is a problem, this is problematic. And so what we do is we want to say something a bit better. We say, okay, we're strongly F-twiddle connected if we've got this property and we don't have any triangle triads. And that leads to, I'll just give you 10 seconds to digest this theorem. And what I'm going to do is I'm going to state this theorem and then I'm going to stop. Right, so what I'm saying this for is to sort of try to say, well, if you work with me and try and follow what I'm saying, you'll get the reward for me shutting up afterwards. But if I feel you're not trying to follow what I'm saying, I might keep going. So I'm going to be looking into your eyes to see who's looking like they're trying to understand. So what are we doing? We started off with a matroid that is our excluded mind. This is the thing we've got in the back of my mind. It's F connected, and it's got equal to. It might as well be equal to 2. That's because no one told us that it was actually we could have had 1. Now, I've got that F prime connectivity. That's the connectivity I'm given, and what this is saying is, yeah, okay, I don't know if I can do it for that, but I can certainly find a function that dominates my F prime. So these first 2 lines are just saying, yep, I can move to a function that does the same job and that has this. And then it says, oh, you tell me I want to remove n elements and keep strong F twiddle K connectivity, right? And n is as many as you like and K is as large as you like. So you tell me that I want to remove a zillion elements and keep strong F, K, triple K, triple whatever. Then then I calculate this gamma in K, right? And then if I give you, and if I can find this function f such that if the size of the matroid has at least gamma n K elements and has that connectivity, well, if Rhoda's conjecture is false, I can find an excluded minor, which has at least gamma n K elements, and it certainly has that connectivity, so this is good. And what it tells me is I can find an n element set. Have I said that it's an n element set?
No.
Okay. So it's a tau independent n element set. Notice tau independence is really, really important here. And because that's telling me that the cardinality is really, really useful information. And this tangle is the one that comes from the connectivity. And I can, and forget about the second consequence, I could just dualize to get this. And that says that I can remove arbitrary subsets from that set and I don't keep my original connectivity, but for all subsets of this n element set, which is n is, I can keep strong, that should be a twiddle K connectivity for all subsets x of x. And so that tells me, so what this theorem does is it tells me that if Rhoda's conjecture fails, I've got this connectivity which is not a bad sort of connectivity, and I can find an arbitrarily sized set, which is independent in the tangle, that's a bit technical, and I can remove arbitrary subsets of that arbitrarily large set and keep a very, very nice connectivity. And that's where I'll stop. And that's, I guess I got through about a third of what I would have liked to. So I'll leave it there.
Thank you. Questions?
So you've talked about strongly F-twiddle connected or F-twiddle K connected to cope with the difficulty of these triangle triads. Could you get around the triangle triads by just perturbing F-twiddle so that F-twiddle of 1 is now 2 instead of 3? Is there a reason for not doing it that way?
Yeah, the reason is that I don't want to do it this way.
Yeah.
Right. I mean, what I would love to do is not have to I'd love to say, oh, I can find a subset X that's independent in the tangle, blah, 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 and that I just keep my original connectivity.
Yeah.
And not have to do the twiddle and the strongly twiddle. But the proof techniques that we've got, and actually I think I even had an example. The proof techniques that we've got mean that these things
So
just
F-twiddle,
arise.
F-twiddle really is the function that you want. You need to have F-twiddle.
Yeah, F-twiddle is the best you can do. I mean, I've got a lemma, and I can prove that lemma. And effectively what happens is this, that you get a large set of elements that you can remove and keep you're essentially keeping F connected, which is K sneaks in, but forget about the K. You get a large set of elements you can remove and keep F connected. Now you've removed all of those elements and you've got F connected. But what you want to say is that I want to remove arbitrary subsets in between the thing. Now I can't say that I can keep, so it's a bit like what Carolyn was talking about. Here I am, I've got some connectivity up here, and I've got some connectivity down there, and I want to say, what can I say about the connectivities in between? And I can't keep the actual connectivity that I care about in between. But so the closest thing I can keep is this F-twiddle connectivity. And if you think about the issues that arise in exact sort of things, you'll see that it'd be unlikely that I could ever do any better than that. I've just got to find the nicest connectivity that I can keep in between. And that actual lemma that tells you that's not a difficult lemma.
So what do you need to be able to remove whatever sets that's contained in your X, say there, right? So you want this to be able to start a continuity between anything that's in between this.
Yeah.
Would you be able to do something where you don't need everything, but you can be a bit more?
Well, the thing is, you don't want to be particular.
So, okay.
So what happens is that, so I start off with my excluded mode, it's got this F connectivity. And then there's another lemma that I would talk about if I had more time, which says that there's this massively large set of elements that I can remove, which is as large as I like, right? I mean, I set the functions up. And I can remove that set and keep the actual connectivity that I had to start off with. But now, that's not what I need. What I need is to know about, and it's all just deletion, by the way. We're not talking about deletion and contraction. So it's not as difficult as, I mean, there's this nice thing because we can sort of, because we're qualitative, we can take majority arguments all the time. So everything's just deletion. So I find this large set of elements I can just delete and keep this nice connectivity. And then I said, but then I have to, but when I go to use this, something else tells me that, oh no, but that wasn't the set I wanted to remove. I want to remove some subset of this because I wanted to keep some other properties, not just connectivity. And so, you know, I wanted to keep unique certain representative. And so I can't declare in advance what that subset is. It's just the subset that gets given to me when I apply these other lemmas. There exists, and then I want to know when for those subsets that I've got a nice connectivity. So, and that's not always going to be the case. Like, so I've got to also say that I can find a subset that I can remove that's got the property that all of the intermediate subsets have some reasonable connectivity. And that's where this strong F-twiddle K connectivity comes up. It's an artifact of the proof as the best connectivity that you could ever hope to keep in these intermediate guys.
You said you're taking the majority argument here. Is there a particular?
Not here, I'm not. I don't.
Not here. You,
Um,
is there? There's no Ramsey argument that underlies the fact that you can separate those two outcomes from a
oh,
single messier
sorry.
outcome.
It's not quite a majority thing. The funny thing is that you actually, the actual proof goes, you find a set C and you find a set C and D that you can delete and contract, and to keep FK connectivity, and then you're deleting and contracting some. Now there's a question of whether you've got more contract things than deletion things, and obviously up to duality you can say you've got more deletion things, but that majority argument doesn't quite work, because sometimes you actually get the win by converting contraction elements into deletion elements. So it's a sort of like, there's majority things crop up in the proof, but it's not a simple majority.
But is there like a strong Ramsey theorem you're using to get to this outcome?
No, I don't think so, no. No, there isn't.
Thank you, Geoff.
Early in the